All right, so here is your review for Unit 1. So we're going to go through most of these, not every single one of them, because, like, for example, this first one, know your vocabulary from the unit. I'm not going to go over every single piece of vocabulary from the unit. So some of these we are going to skip, but most of them we are going to go through. So as we go through them, follow along. So this first one, I'm not going to read the whole thing to you, but a guy made a bet about a horse, okay? So you can read through that at your leisure, but that's what happened. Now, the order at which this stuff all happened is based on the scientific method. Okay, so the first thing that the guy did was ask himself a question. So the step one was right here. Mr. Stanford wondered if there was some point in time during the gallop that the hooves of a horse don't touch the ground. Okay, so that was his first step. That was the question that he asked himself. Okay, next he made the bet. So that's this one here. Leland Stanford made a bet that there is blah, blah, blah. You can read. So after he made the bet, he decided to test that out. He would ask a photographer to take some pictures of the galloping horse. So next one is that one. He asked the photographer to take some pictures. Okay. After he asked the photographer to take some pictures, then the horse had to actually go around the racetrack. So next is that one. Okay. Now, while the jockey was rode the galloping horse around the racetrack, the picture guy was taking the pictures. So next is that one. Okay. And then after that, some of the pictures showed that the horse's hooves were all in the air at the same time. So last is that one right there. Okay. So scientific method, you're just looking at the logical order of when things happen. Okay. Next, what is the difference between qualitative and quantitative? Okay, now qualitative is an observation that is describing the quality of something. So, for example, color, relative size, anything like that. Basically, anything that does not include a number. Okay, color is the most common one generally. Quantitative. Okay, that base word is quantity. So a quantitative observation is an observation that does include numbers. Okay, so for these different examples down here, I'm just going to circle the quantitative ones. So quantitative is anything with numbers. So that's going to be A, because we have an object's mass of 2.3. So basically anything that is measured is going to be a quantitative observation. Okay, and then letter E gives you the temperature of something. Okay, all these other ones, carbon dioxide was produced, the liquid turned yellow, a yellow solid is formed. None of those things have numbers in them. So those are all qualitative, and the circled ones are quantitative. Okay, all right, difference between an observation and inference. So an observation is anything that you can perceive with any of your five senses. Okay. An inference is using prior knowledge to make a statement about something. Okay. So an observation is just anything that you see, feel, taste, touch, or smell. Okay. You cannot make an inference with your five senses. You have to use previous knowledge, and a lot of times inferences are based on observations, but they are not. You can't make them with just your five senses. You need more information than just your five senses to make an inference. Okay, so next we're going to classify each of the following as an observation or an inference. Now, this can be a little tricky sometimes, so be careful. When the dinner with her husband's parents was over, she was so anxious to leave and go home that she left her coat behind. Okay, so you can definitely make an observation that she left her coat behind, but can you make an observation that she left her coat behind because she was so anxious? Can you see, touch, taste, feel, smell that she was anxious? No, you can't. You can observe that she's twiddling her fingers or sweating or something like that. So that would be an observation that she was doing one of those things. But you would make an inference that since she is doing those things, she is anxious. That would be previous knowledge that you know you generally know people, when they are anxious, they twiddle their fingers or sweat or whatever. So that first one is definitely an inference. Okay, so next one. He beeped the horn several times in rapid succession, turned into the oncoming lane, and sped around a stalled car. Now, this one is tricky. Okay, so almost all of these things are definitely observations. He beeped the horn. You can definitely hear and see that in rapid succession. For sure, you can hear that. Turned into the oncoming lane. You can definitely see a car turning into a lane. And sped around a stalled car. You could see the car speeding up. But this right here is the key word, the stalled car. Okay, that makes this an inference because you can't observe a car to be stalled. You can observe a car to be stopped. You can observe maybe some smoke coming out of the hood, but you can't observe a car to be stalled. You can infer that because it stopped and because there's smoke coming out of the hood, it must be stalled, but you can't make that observation. So that's why I said this is a really tricky one, because that a lot of people would probably just read right over that stalled car part and just say, oh yeah, that's an observation because of all the other things in this. But that one word makes it an inference instead of an observation. So okay, next is accuracy and precision. Okay, so this has probably been a tricky one for a lot of people because it's not really very well defined. So accuracy is if you get the correct answer or if you hit the target properly. So if I am measuring a pen and the pen is actually 7 centimeters long, and I measure the pen and I say it's 6.9 centimeters. Okay, that's pretty accurate. Okay, it's not perfect because it's 7 instead of 6.9, but that's pretty accurate. Okay, now if I said the pen is 12 centimeters long, that's not really very accurate, right? Now precision is different. Precision is repeatability and consistency. So, for example, if I were to take that same pen and I were to give it to 10 different people, and all 10 of those people said, this pen is 12 centimeters long. Now, first of all, is that precise? Yes, it is, because all 12 of those people made the same measurement. It's repeatable, it's consistent. Now, is that measurement accurate? No, it's not, right? Because the pen was 7 centimeters long. So it wasn't accurate, but it was precise. Remember, precise is consistency, okay? You don't necessarily have to be accurate in order to be precise. Okay, the science department, you can read. All right, so we are going to name all the different parts of this this experiment. So one half of LTHS was one group at LTHS was given the brain pill. One group was given an identical looking pill, but without the brain stimulating ingredients. So that group, the group that got the brain pill, but did not get the actual active ingredients, that was the control. They were not getting the independent variable applied to them. So they are the group that you're going to compare the experimental group to, which is why we have a control group, so that we can compare the experimental group to them. Okay. Okay, so the constants are, again, anything that stays the same. Okay, so anything that stayed the same in this experiment is a constant. So some of the explicit constants that we used in this experiment were the students were given the pill with 8 ounces of water at the same time every day for an 8-week period, and the staff was told exactly what lessons were to be taught. Okay, so they had the same amount of water, they were given it at the same time every day for an 8-week period, and they were all taught the same lessons. Okay, so again, anything that stays the same in an experiment. Okay, so next is the independent variable. Now, the independent variable, again, is the thing that we are testing, the thing that we are manipulating in the experiment. So in this experiment, the thing that we are testing is the brain pill. So the brain pill is our independent variable, okay? And then last, the dependent variable. So the dependent variable, in simple terms, is your results, okay? Whatever the results of your experiment are, that's your dependent variable because it depends on what your independent variable does. So in this case, the dependent variable was if the student's brain power increased, if their test scores increased, okay? It doesn't actually say exactly how they were checked, but whatever the results of them being checked were, that was our dependent variable, okay? Okay, so here we are going to make a graph. So we have age of the tree in years, okay? Average thickness of A, average thickness of B. Now, when we make a graph, the independent variable is going to go on the x-axis. So x-axis is the bottom axis down here. This is the y-axis up here, okay? So our independent variable is age of the trees in years. Okay, this is what we are testing. All right. So we're going from 0 to 60. So when you are determining how often to mark your axes, then you want to make it so that the graph is spread out for the whole, or your data is spread out for the whole graph. You don't really want to have very much empty space. You can have a little bit, but the less amount of empty space, the better. So on this bottom part, I am going to put a 10-year mark every 2 spaces. So 10, 20, 30, 40, 50, 60. Okay, so there is a little bit of empty space over here, which is not ideal, but that's the best we can do. And sometimes that's all you can do. All right, so now for this other one, this is a little bit longer. So we are going to pause the video for a second, and I'll show you what I did after that. Okay, so I paused it and just did it so you didn't have to watch me do the whole thing, but this is what I did. I marked 1 centimeter. Yeah, centimeter every 6 lines. And that way, since our maximum is 4.5 right there, okay, we almost hit the top of the graph. Not quite, but again, a little bit of empty space is okay, but we just want to minimize that. Okay, so next, we're going to start plotting our line. So the first one, at 10 years, we have 2.0 centimeters. So there's 10 years, and there is 2.0 centimeters. Next, we have 2.2, and that's at 20 years. So we'll go down to 20, 2.2, right about there. Next, at 30 years, we have 3.5. So 30, we go up to 3.5 right there. Next, we have 40 at 3.0. So that went down a little bit. So 40, 3.0. 50, 4.5. Right there. And 60, 4.3. So again, that went down a little bit. Whoops. 60, 4.3. There we go. So that's, which one is that? That is the average thickness of forest A. So now we're going to connect those dots. All right, so that's forest A. We're just going to label that. We'll say right there. Okay, so next we're going to do forest B. So at 10 years, we got 2.2. So 10 years, 2.2 right there-ish. Then 20 years, 2.5. 2.5. Then 30 years, 3.6. 3.6. 40 years, 3.8. 50 years, 4.0. And 60 years, 4.5. So now we're going to connect those dots, and this time, since we did a solid line last time, we'll do a dotted line this time. Put that A in an inopportune spot. Just like that. So that is forest B. Okay. So that is our graph for that. Okay, so that takes care of number 11. What is the dependent variable? So our dependent variable, again, is our results, right? So our dependent variable is going to be the average thickness of the annual rings, whether it be forest A or forest B, it's just the annual thickness. The independent variable is how many years it takes, because we make a measurement at each 10-year interval. So we are controlling that. What is the average thickness of an annual rings of 40-year-old trees in forest A and forest B? So for 40 years, it's 3.0 for forest A, 3.8 in forest B. And then based on this data, what can you conclude about forest A and forest B? So first off, forest A is kind of a roller coaster, right? It goes up and then it goes down and then it goes up and then it goes down a little bit. So forest A is a little bit less consistent and also ends up a little smaller. Forest B is more consistent. It's going up the whole time and it ends up bigger. So forest B overall generally has thicker rings. Forest A has 1 year where it's way thicker, but every other year it's not as thick and it ends up not as thick. So that is our conclusions. All right. Which digits are recorded when making a measurement? How does the number of digits in a measurement relate to the device it was measured on? Okay, so digits that are recorded. Always we record our certain digits. And then we record one uncertain digit. Okay. As far as measurements go, it doesn't really, there's no limit on certain digits you can have, or there's no maximum. There is a limit on uncertain digits. It has to be one. It cannot be less than one. It cannot be more than one. It also always has to be one uncertain or estimated digits. Okay. That uncertain digit is always one place value past whatever your measurement tool is marked to. So if it's marked every 1 centimeter, your estimated digit has to be in the 10th place. If it's marked every 10th of a centimeter, your estimated digit has to be in the 100th place. Okay. All right. How does the number of digits in a measurement relate to the device it was measured on? Yeah, we talked about that. Okay, cool. So next we have a few measurements. So this first one, our measurement is between so actually first, let's talk about how often this is marked. It's labeled every 1 centimeter, right? But it's marked every 10th of a centimeter. All these smaller lines that don't have numbers on them, those are tenths of a centimeter. So that means our answer has to be in the 100th place. Now, our certain digits are going to be, so here's 15 right here. It's definitely after 15. It's definitely before 16. So 1, that's 6. I don't know why I did that, but 1, 5. There we go. 15, those are our certain digits. Okay, now we also can tell that it is before the 0.1. Okay, it's definitely before the 0.1. So our next certain digit is going to be a 0 because we are sure that it is less than 15.1 centimeters. Now, those are certain digits, okay? This is, again, marked every tenths place, so we have to go to the hundredths place. Now, this place, it's going to be, like, it depends. Like, I am going to say 15.05 because I estimate that's right about in between the 15 and the 0.1, okay? If you were to say 15.04, that'd be fine. If you were to say 15.06, that'd be fine as well, okay? Again, it's estimated, so it's going to be different for everybody, okay? Now, one thing we are missing, units. Can't forget your units. Always put your units, okay? All right, so next we have a graduated cylinder. Now, that is measuring liquid, right? And when you're measuring liquid in a graduated cylinder, you have to look at the meniscus. So as you can see, the meniscus kind of curves down like that a little bit. That is not where the meniscus is. I'm just giving you an idea of the shape. But the meniscus is right there. So it looks like it's right about on that line right there, which I put a dot a little bit below that line. I did not mean to. But anyway, so each of these lines are going to be 0.2 milliliters. Okay, so it's here we have 7.2, 0.4, 0.6, 0.8, and 8. Okay, so since that is right on the 0.6 mark, okay, then our certain digits are going to be 7.6. Okay, and I'm going to just say 7.60 because I think it's right on that mark. If you were to say 7.61, that would be fine, okay? Or if you were to say 7.59, that would be fine. Now, last thing, milliliters, okay? All right, last reading, we have grams this time. So here we have our 100, and that looks like 130, and that's 137, and that's 137.4 because it's between the 0.4 and the 0.5. So those are all our certain digits. Okay, so 137.4. Okay, then we have even more small markings down in here. So that those are by hundredths. Okay, so that's smaller than the point or the tenth. So that looks like it's in the 1 or 5, 6, 7, 8. So it's after the 8, but before the 9. So that is where it's marked to. It's marked every hundredth of a gram. So we have to go one place value past that. So I'm going to say that's pretty close to the 8 and not as close to the 9. So I'm going to say that's 0.482 grams. Again, that's your estimated digit. So you can say some different things, but that's what I am saying. Okay. All right, next we got sig figs. Okay, so remember our 3 rules of sig figs, okay? Any non-zero digit is automatically significant, no exceptions, okay? Next is our zeros, okay? So we have 2 types of zero. I'm sorry, we have 3 types of zeros. We have leading zeros, we have trailing zeros, and we have sandwich zeros, okay? Leading zeros are never significant. Sandwich zeros are always significant, and trailing zeros are significant if there is a decimal somewhere in the number. Okay, so this first one here, we have 1 and 6. Okay, those are definitely significant because they're non-zeros. That was a bad line. That is a trailing zero. Okay, and since there is a decimal right there, that means that trailing zero is significant. So this is going to have 3 sig figs. This one here, the 5 and the 4 are significant. They're non-zeros. And then these 3 are trailing zeros. But this time, there is no decimal in the number. So those zeros are not going to be significant. So this is going to have 2 sig figs. Next one, it looks like the same number, right? But that decimal is very important, okay? That decimal makes all of these trailing zeros significant now. So that is, all of those are significant. So we have 1, 2, 3, 4, 5, 6 sig figs. Okay. Next one, all of these zeros, they are leading zeros, which means they're not significant. That zero is a sandwich zero, which means it is significant. So this has 3. Next one, those zeros are sandwiched. They are significant. So that's 4. Next one doesn't even have any zeros. So that's nice and easy. 2. All right. Next, we are changing numbers into scientific notation. So remember, scientific notation, you have to move the decimal so that it's after the first non-zero digit. So in this first one, 123 billion, that the first non-zero digit is the 1. So 1.23, okay, times 10. And now we have to figure out how many places we move the decimal. So here's where the decimal is right now. We have to move it until it's there. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So we moved it 11 places. So that means it's times 10 to the 11th grams. Okay. Now, since this is a really big number, and when I say big, I mean bigger than 1, that means this 11 is going to be a positive exponent, not a negative. Now, on this next one, first non-zero number is the 5. So 5.44, there we go, 06 times 10. Now we have to look at how many places we move. So zeros are decimals there. 1, 2, 3 places. So it's times 10 to the 3rd. Now, since this is a small number, and when I say small, I mean smaller than 1, that means our exponent is going to be negative this time. Okay, and that is megagrams. All right, next one, 105,000 milliliters. So again, 1 is our first non-zero number. So 1.05 times 10. Here's the decimal, 1, 2, 3, 4, 5. So it's times 10 to the 5th. And since this is a big number, 5th stays positive. And that's milliliters. Last one, we put our 6.4 times 10. We move our decimal 1, 2, 3, 4, 5 places. And since this is a small number, that's going to be a negative 5 seconds. All right, so now we got to do the opposite. We're taking them out of scientific notation, okay? So we are going to do the opposite of what we're doing. Since this one is a positive 4, then that's going to be a really big number. So we take that decimal, we move it to the right 4 places. So that's 1, 2, 3, 4. Put our comma, and it doesn't give us units. So that's it. Okay, so next one is a negative exponent. So this time we're moving the decimal the other way. So we take the decimal, we move it 7 places. 1, 2, 3, 4, 5, 6, 7. We fill each of those places with a 0. So it's going to be 0, 0, 0, 0, 0, 0. There we go. So that's going to be 1, 2, 3, 4, 5, 6, 0. So 1, 2, 3, 4, 5, 6 zeros, 6, 5, 2, 1. And that's our number. Next one, same situation, but we move it 3 places. So 1, 2, 3. So it's going to be 0.0048. And last one, we're going to move it to the right this time because it's a positive exponent. So 2, 1. Whoop, I don't know why I wrote a 1 there, but 2 places. So it's going to be 210. Okay. All right. So this next part, I'm not going to do because I can't really show you how to do it on a calculator on this video, but make sure you remember to press the EE or the EXP button on your calculators. Do not type times. Do not type 10. Do not type caret. Okay, the EE or EXP button completely replace all of that. Okay. All right, metric prefixes. So that is all on your chem packet, but we have king, hector, dector, baked, delicious, cookies, Monday, and also my fault, this should be a capital D. Okay, so K is killa, hecta, deca, base unit, so that's grams, liters, and meters, deci, centi, and milli. Okay, now there is also micro and nano, and then on this side, there's mega. Now, all of these ones in the middle, they are one place value away from each other, but micro, nano, and mega are all 3 places away from the next thing. So if we're going from milli to micro, we have to move 1, 2, 3 places. If we're going from micro to nano, 1, 2, 3 places. If we're going from killa to mega, 1, 2, 3 places. Okay. All right. So I should probably leave that up there. If we have 89.75 kilograms to centigrams, then we first have to find kilograms. Right there. Then we have to find centigrams right there. Then we have to determine how many places is between them. So 1, 2, 3, 4, 5. So 5 places, and we moved from the left to the right. So we have to do the same thing with our decimal. We have to move it from the left to the right. So if we have 89.75, we have to move it 1, 2, 3, 4, 5 places to the right, fill in those places with zeros, and that's our new number. Don't forget units. Okay? All right, next, centimeters to meters. So again, we have to find centimeters, which is again right there. We have to find meters, which is the base unit. So we only have to go 1, 2 places. So we're going 2 places to the left. So 165. Decimals right here. We go 1, 2 places to the left. Our new number is 1.65 meters. Okay. All right, next, megaliters to hectoliters. So here is megaliters, here is hectoliters. Okay, now remember when we're going from mega to killa, that's 3 places. So 1, 2, 3 to killa, 4 to hecta. So we got to move it 4 places to the right. So if we have 0.056, 1, 2, 3, 4. Fill in that 0. So our new number is 560 hectoliters. Last one. Oh, that's not what I meant to do. 560 hectoliters. There we go. Okay, so last one. We have micrograms to decagrams. Okay, so first we have to find micro right there. Next we find deca right there. So we go 1, 2, 3, 4, 5, 6, 7 places, and we're moving to the left. So 0.0046, we move it 7 places. 1, 2, 3, 4, 5, 6, 7. That's going to be our decimal. Fill that in with zeros. And that's our new number. A whole bunch of zeros. Point, a whole bunch of zeros. 46 decagrams. All right, so last and not least is density. So what is the density of an object that has a mass of 67 grams and a volume of 14.7 milliliters? So when we're doing this, we got to remember the formula for density is D equals M over V. Okay, so next we have to identify our parts, what we have. Okay, so grams, that's always going to be mass. So our mass is 67.0 grams. It says volume here, and it gives you milliliters, so that's our volume. So V equals 14.7. Sorry, that's a really bad 4. There we go, that's better. Milliliters. Okay, so now, since our formula is just D equals M over V, we put our mass, 67, there we go, 0.0 grams divided by 14.7 milliliters. And we get 67 divided by 14.7, 4.56 grams per milliliter. Okay. All right. Next one. What is the density of an object that has a mass of 17 grams? So mass equals 17.0 grams and is a cube with the dimensions of 1.2, 7.4, and 3.0. Now, since this is a cube, we can take these measurements and use the volume formula for a cube, which is length times width times height. So if we do that, we get a volume of 26.64 centimeters cubed, since we're taking centimeters times centimeters times centimeters. Okay. Now, again, this is nice and simple. We have our mass and we have our volume. So we take 17.0 grams divided by 26.64 I think my pen's running out of battery or something. Centimeters. Centimeters. There we go. Cubed. And we get 17 divided by 26.64. And we get 0.638 grams per milliliter. All right, next, I'm going to write this formula down again. What volume will 88 grams of an object, so 88 grams, that's our mass, of an object with a density of 3.44 grams per milliliter. So this time we don't have volume, we have density. So this time we have to rearrange our equation, okay? So we have density. So that means we have to get volume by itself. Now, I'm going to write this over here so I have more room. Density equals mass over volume. Okay, so we have to get volume by itself. Now, to do that, first, we multiply both sides by V, like that. That will cancel out our V, and we're left with VD equals M. Now, that still doesn't really help us, right? Because we want V by itself. V is still not by itself. So we got to do something else. We have to divide both sides by D. That way, D cancels out over here, and we're left with V equals M over D. So now we just take M, 88.0 grams, divided by D, 3.44 grams per milliliter. And we get a number that I haven't calculated yet, so give me a second. 8 divided by 3.44. We get 25.6 milliliters. Okay, and it's milliliters because grams cancels out, and we're left with milliliters on bottom of the bottom. So that's actually just regular milliliters. Okay. All right, last one. What would be the mass of 0.47 liters of a substance with a density of 8.73? So this time we have liters. So that's volume. 0.47 liters. And we have density, which is 8.77. There we go. 3 grams per milliliter. Okay. Now, this is a problem, right? We have gram per milliliter, and here we have liters. That's bad. So first thing we got to do is convert our liters into milliliters. Now, since we know that on the metric number line, liters is a base and milli is to the right 3 places. I'll scroll up a little bit so we can look at that right there. So liters is a base, milli is to the right. Okay. We want to move our decimal 1, 2, 3 places to the right. So that's going to be 1, 2, 3 places. So that's going to be 47 milliliters. Okay. Now we have to rearrange our equation. D equals M over V. Now again, this time we have density, but we don't have mass. So we got to get mass by itself. So we're going to first multiply both sides by V. V will cancel out. And look at that. We have mass by itself. So that's all we have to do. So this time we're just going to multiply 47 by 8.73. And we are, I probably should have written that down. 8.73 grams per milliliter times 47 milliliters. And we get 410 grams. And that's our answer. And that is your entire review. Hooray!